Before we start this journey, just quickly hit that subscribe button. It's free, and you only have to do it once. Let's start this journey. Unveiling the Laden Effect. Imagine a river carrying sediment. The water isn't just flowing, it's laden with particles that affect its every movement. This is the Laden Effect, where suspended particles dramatically alter the behavior of fluids. Think about dust in the air, influencing cloud formation and climate. Or consider blood flow, where red blood cells navigate a complex vascular network. Section 2. The significance of suspended particles. Particles in a fluid don't just travel passively, they interact with the fluid and each other. These interactions impact the fluid's density, viscosity, and flow. Smaller particles increase viscosity, making the fluid more resistant to flow. Larger particles influence flow patterns, leading to turbulence or sedimentation. Understanding these interactions is crucial in fields, from pollution control to industrial processes. Section 3. The impact of particle size. Imagine stirring fine sand into water versus gravel. Sand disperses, creating a murky suspension, while gravel settles quickly. Smaller particles have a larger surface area, increasing fluid viscosity. Larger particles influence flow patterns, causing turbulence or settling. Particle size dictates behavior in response to external forces. Smaller particles are more susceptible to Brownian motion, while larger ones are influenced by gravity and fluid flow. Section 4. A numbers game. Particle concentration refers to the number of particles in a fluid. Low concentration has minimal impact, while high concentration increases viscosity and alters flow. At very high concentrations, particles interact, forming complex networks. This can lead to dramatic changes, like the formation of gels or quicksand. Understanding concentration is crucial in applications from paints to mudslides. Section 5. Size and concentration. Particle size and concentration work together to influence fluid behavior. High concentration of small particles increases viscosity, creating a thick substance. Low concentration of large particles influences flow patterns, causing turbulence. The interplay between size and concentration dictates fluid stability. This knowledge is crucial in fields from drug delivery to volcanic ash prediction. Section 6. The stickiness factor. Viscosity is a fluid's resistance to flow. Suspended particles can dramatically alter viscosity. Smaller particles increase viscosity by creating more friction. Larger particles influence viscosity based on concentration and shape. The type of fluid also affects how viscosity changes with the Laden effect. Section 7. The balancing act. Density measures how much mass is packed into a volume. Suspended particles add mass, altering fluid density. Higher particle concentration increases fluid density, impacting flow and erosion. Density differences between particles and fluid affect sedimentation. Understanding density is vital in applications from mining to wastewater treatment. Section 8. Other fluid properties. Suspended particles affect more than just viscosity and density. Optical properties change, like clear water versus cloudy milk. Thermal properties can be enhanced, useful in cooling electronics. Electrical conductivity is altered by charged particles, important in batteries and sensors. Understanding these interactions unlocks technological advancements. Section 9. The interface of influence. Surface properties of particles influence their behavior in fluids. Surface roughness affects drag force and settling velocity. Electrical charge impacts particle distribution and clustering. Chemical composition dictates wettability, influencing dispersion or agglomeration. These properties are crucial in industrial processes like water treatment. Section 10. A love-hate. Relationship with fluids. Wettability describes a material's affinity for water. Hydrophilic particles disperse readily, forming stable suspensions. Hydrophobic particles aggregate, forming clumps. Wettability can be manipulated by altering surface chemistry. This is important in applications from drug delivery to industrial processes. Section 11. Aerosols and atmospheric dynamics. Our atmosphere is filled with aerosols, tiny particles influencing climate and air quality. Aerosols impact Earth's radiative balance, cooling or warming the atmosphere. They influence cloud formation and precipitation patterns. Fine particulate matter affects air quality, causing health problems. Understanding aerosols is crucial for mitigating their harmful effects. Section 12. Sediment transport and river morphology. Shifting sands. Sediment transport and river morphology. Rivers, the lifeblood of many ecosystems, are masters of the Laden Effect. They carve landscapes, transport nutrients, and shape habitats. Central to these processes is the river's ability to carry sediment. The sediment load depends on flow velocity, volume, and sediment characteristics. Fast rivers transport large boulders, while slow rivers carry fine silt and clay. Meanders form from the Laden Effect. Water erodes the outer bank and deposits sediment on the inner bank. Deltas form as rivers deposit sediment near the sea. Understanding sediment transport is crucial for managing water resources. Section 13. Tailoring properties with nanoparticles. Engineered composites. Tailoring properties with nanoparticles. From the lightweight frames of aircraft to the high-performance components of sports equipment, composite materials have revolutionized engineering. These materials, formed by combining two or more distinct materials, owe their exceptional properties to the Laden Effect, specifically the strategic incorporation of nanoparticles. Nanoparticles, with their incredibly small size and high surface area to volume ratio, can dramatically alter the properties of a base material when added even in small quantities. This ability to tailor material properties has opened up a world of possibilities in material science and nanotechnology. Carbon nanotubes, for instance, are incredibly strong and lightweight, making them ideal reinforcements for composite materials. When added to polymers, they create a network of interconnected fibers that enhance the material's strength, stiffness, and toughness. Similarly, adding nanoparticles of titanium dioxide to paints and coatings can create self-cleaning surfaces. Titanium dioxide acts as a photocatalyst, using sunlight to break down organic pollutants and dirt, keeping the surface cleaner for longer. The Laden Effect, in the realm of engineered composites, allows us to move beyond the limitations of traditional materials, creating lighter, stronger, and more functional materials for a wide range of applications. Section 14, Cell-Laden Hydrogels in Bioengineering. The living matrix. Cell-laden hydrogels in bioengineering. The human body is a testament to the intricate interplay of cells, tissues, and fluids. Bioengineers use cell-laden hydrogels to mimic the body's natural healing processes. Hydrogels, networks of cross-linked polymers, provide an ideal scaffold for cell growth. By seeding these hydrogels with cells, researchers create artificial tissues. The mechanical properties of these hydrogels are crucial for tissue replacements. The type of cells and their density influence the artificial tissue's properties. Cartilage can be engineered using hydrogels laden with chondrocytes. Chondrocytes secrete extracellular matrix, reinforcing the artificial cartilage. Cell-laden hydrogels hold immense promise for regenerative medicine. Section 15. Navigating Fluid Dynamics. Key parameters. Understanding the Laden Effect requires delving into the realm of fluid dynamics, a field that explores the motion of fluids and how they interact with their surroundings. Key parameters like signposts on a map guide us in comprehending the complex behavior of laden fluids. Reynolds number, a dimensionless quantity, helps us predict whether a fluid flow will be laminar, characterized by smooth, orderly movement, or turbulent, marked by chaotic, swirling eddies. This distinction is crucial in understanding how particles will disperse and interact within the fluid. Imagine a gentle stream flowing over smooth pebbles. The flow is likely laminar, with particles moving along predictable paths. Now picture a raging river cascading over boulders. The flow becomes turbulent, with particles tossed and turned in unpredictable ways. Particle settling velocity, another crucial parameter, dictates how quickly particles will settle out of a fluid due to gravity. This velocity depends on the particle's size, density, and shape, as well as the fluid's viscosity. Understanding settling velocity is crucial in various applications. In wastewater treatment, for instance, controlling settling velocity is essential for removing suspended solids. In paint manufacturing, ensuring a slow settling velocity helps maintain a uniform pigment distribution. Section 16. Interfacial tension, the delicate balance at boundaries. At the interface between a liquid and a gas, a delicate dance of forces plays out. Interfacial tension, arising from cohesive forces, influences particle behavior. These forces create an inward pull, minimizing surface area. Hydrophilic particles reduce interfacial tension, aiding spread. Hydrophobic particles increase it, causing beading. This principle is crucial in waterproof coatings and drug delivery. Section 17. The unseen world shaping our reality. From the dust that dances in a sunbeam to the intricate machinery of our own cells, the Laden Effect is a constant, often unseen force shaping our world. It highlights the interconnectedness of matter and motion, reminding us that even the smallest particles can have a profound impact on the behavior of fluids. Understanding the Laden Effect is not just an academic pursuit. It's crucial for addressing some of the most pressing challenges facing our planet. From predicting the spread of pollutants in the atmosphere to designing sustainable water treatment systems, our ability to manipulate and control the Laden Effect will be paramount in creating a healthier and more sustainable future. As we've journeyed through the fascinating world of suspended particles and their influence on fluids, we've seen how this seemingly simple phenomenon underpins a vast array of natural processes and technological advancements. The Laden Effect, in its subtle yet pervasive influence, serves as a constant reminder that the universe is full of surprises and that even the most seemingly insignificant particles can hold the key to unlocking a deeper understanding of the world around us. Thank you for watching, all you science nerds, and have a beautiful day, and stay scientific, my friends.